is that I want to ask a simple question. What is a force? So what I'm going to do here is that I'm going to go through a series of questions or a series of remarks. And I think that there's, I don't know, 3 or 4. I'll make it up. I don't know how many I'm going to go through, but I don't want to get too detailed because we still got to really talk about forces in general. So the first thing that I would ask here says this: a force is a push or a pull on an object. And this is an important one. Okay? This is an important one. And what this push or pull really do here, what they do here is that it's a specific action. So I want to say this even stronger. If it's not a push or if it's not a pull, it's not a force. In fact, there are people like, oh, there's a suction force. Guess what? There's no such thing as a suction force. It's a push or a pull. Nothing else. It's that simple. And then this one becomes a really important one. And the reason why this becomes, it's all 3 of these that I got to say, because you sort of have to really focus on these things to really identify what a force is. A force acts on an object. So that means I have a block, okay? Let's say that I have a block. And now this block here, what we want to do here is that this is my object, right? Here's my object. So that means if I have a force, it has to act on something. So that means here, I'm going to come in and I'm going to apply a force to an object. You can't have a force if it doesn't apply a force to an object. 3, a force requires an agent. And in other words, this is really the basis to cause and effect. Okay, requires an agent. That's a big one here. Because this is the when people are making up fictitious forces, what you're going to see here is that they won't be able to identify what the agent is that's going to apply the force here. So as some simple examples here, let me give you a couple of things. So in other words, what we need here is that we need an identifiable cause or agent on an object. Okay, there has to be an identifiable cause or agent on an object. Okay, here's 2 simple examples just to give you a sense of what I mean by this. So let's say that you're going to throw a baseball. Well, here's the baseball. What do you got to do to throw the baseball? What you do here is that you have to pick it up with your hand and you have to apply a force with your hand. So in this case, the hand is the agent to apply a force on the ball. So clearly the hand's the agent or the cause. But let's go back to our previous example. So if we're talking about a previous example, let's say that you're suddenly stopping in a car. And we just went over this here. And what we said here is that I have a car situation. And then here's my car. And what's happening with the car here is that the car now is slowing down. So that means when I look at the speed of the car, it's moving at 40 miles an hour, but the speed of the person is 50 miles an hour. So if you're in the car, what actually happens? The person, right, feels as if something is pushing, right, on them. Question: what's the agent in this case? And the answer is nothing, right? There's nothing. There's no cause. And because of this, you'll see sometimes in physics, they'll call this a pseudo force. There's nothing causing it. I cannot tell you how many times people will say, oh, that's the momentum force. Guess what? Momentum's not a force. Oh, that's the force of the mass. Guess what? There is no force of the mass. And you got to be really careful because there's a lot of stuff that you're bringing in that doesn't match up with what is the definition of a force. And then the last thing that we should talk about is that there's two kinds of forces.
Hey, Carlos,
Yeah.
what does an agent have to be? Like, what's the definition of an agent? Because why isn't the braking the agent for the car?
The brakes don't act on the person.
Oh, yeah.
The brakes act on the tire. So
Okay.
what's the force pushing that person forward? There isn't anything.
Yeah. So the agent can be anything. It just has to be acting on what
It
we're
has
talking about.
that, and you could see that I'm trying to be very careful here. The force acts on an object.
Okay.
Is there something acting on that person in the car? The answer is no.
Okay, got it. Thank you.
And so and then this will help clarify your question. There are two classes of forces. There's contact forces and long range. So a contact force, so if we look at contact force, are forces that act by touching. And what you're going to find here is that this is the vast majority of forces we deal with. Long-range force I should put in as the long-range forces act on an object without touching. I didn't really want to write that. I wanted to write that in capital. Without touching. And a very clear example of this thing would be the Earth. So when you're thinking about the Earth, what we know about the Earth here is that it has the force of gravity. So you could imagine that if I have an object right here, what you're seeing here is that there is a force between this object and the Earth. So what we say here is that the force of gravity is not in contact with an object, unless it's on Earth, but we're talking about it's like in free fall. Okay, so those are the four things that define forces here. So now what I want to do here is that I want to go in and I want to talk about the important thing of force diagram. And so the way we deal with forces, and by the way, note how detailed I am. I'm being extremely detailed because, like I said before, if you're in engineering, this is a big ass deal. This is something that you gotta be a master of. Okay, so now we want to talk about force diagrams. So we need a visualization process of actually doing this. So we want to talk about force diagrams. And when you look at force diagrams, the way we visualize them is probably the most important thing. I don't want to say in the whole course, but pretty damn close. So force diagrams are known as free body diagrams. And these are typically abbreviated as FBD. That's what we want to focus on right now. So to draw a free body diagram, you have to visualize how the forces act on a body. So what we're going to do here is that we're going to draw a free body diagram to visualize how forces act on an object. So what do I mean by this? Well, we could think about, let's say that we have a surface here. And with that surface, we have an object. Let's say that this is my block. And so when I'm thinking about this block here, what we're really looking at here is I have a box, right? So I know I have a box here. And so what I really try to do here is that I try to isolate just the box. So I draw a dash enclosed, circle to isolate the box. So when I do that, then I just say, okay, so now what could be acting on this box right now? So you could imagine that I have this observer here. And what is this observer doing? It turns out that it has a rope. And so when I look at this observer here, what this observer is doing here is that he's going to be pulling on this rope in this direction. So what I'm seeing here is that the green rope is the agent, right? It's the agent. To do what? To apply the force. Now it's very, 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 very common for people to do what? They'll say, no, 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 it's the person who's applying the force. That's not true. That person is not in contact with the box. It is the rope that is in contact with the box. So it's the rope that's applying the force. So then what we do here is that then we reduce, so our job here is to reduce the box to the center of mass. Dot. So that means we take that whole box and we treat that whole box now as a dot. And then we ask, what is actually acting on that? Well, it's the green rope. And which direction is that green rope doing? Well, it has the force of a rope. And in this case, is it a push or a pull? This is a pulling force. So by isolating it and looking at the agent, you have that. Now we can look at other examples. We could also imagine the same box in this situation. So imagine that I have the exact same box. This time I have a wall, and attached to this wall is a spring. So when I go and I look at my box, here's my box, right? There's my box right here. And attached to this, to the wall, is a spring. And what you're seeing here is that this time what we're going to do here is that I'm going to say if I isolate this box, there's only one thing acting on this box here. So we could imagine that we compress this thing. And what I mean by this is that this is a compressed spring. So if it's a compressed spring, what I'm going to do here is that I'm going to isolate my box by the center of mass point. And what I'm seeing here is that the spring is trying to uncoil. So this means a compressed spring wants to uncoil. So what it's going to do this time is it's going to push away. There's multiple ways to write it, but the customary one is to do what? Say that this is the force of the spring on the dot. And of course, in this case, instead of a pull, it's a push. So it's a pushing force. Okay, so moving along in these directions here, what I want to do now is that, what do we know about these things? Experimentally, all objects feel the net force. All objects only feel the net force. And when we say all objects feel the net force, what we find here is that the way they feel the net force is something called superposition of forces. So all objects only feel the net force because of superposition. So what do I mean by that? So what you find here is that you have a series of individual forces. And what I mean by individual forces is that I have F1, F2, F3. You could imagine that I have lots of them. So these individual forces act on an object. So what the superposition principle says it says that the net effect of all of these individual forces is summed as follows. That means here that this thing called the net force is really 1, 2, 3, as many as forces that you have, and that this guy is the single effect that objects feel. They don't feel these guys here. These guys are essentially blurred out. But the only thing that it feels is that guy right there. And so what do I mean by this? So let's imagine that I have a situation that looks like this here. So imagine that I have a block. Okay. So in this case here, I'm going to give you a top view. So here's my block. So here's my block right here. And when I'm looking at this block here, what you're going to find here is that there are two forces acting on this object. So there's a red force, and then there's a blue force. So according to superposition, we could use the parallelogram rule to add these together. So in other words, I can go like this, I can go like that. And what I'm seeing here is that there's one single force. And this thing, by the parallelogram rule, is really this F1, F net, which is, of course, the sum of both of those forces here. So instead of, so like I said before, this block does not feel F1 and F2. So what I can do here is that I could come over here and just say, okay, what's really happening here? What's really happening here is that this thing feels what? It feels this guy right here. It feels this net force, which is what? 1 plus 2. It does not feel that. It only feels that net force. So when we talk about resistive forces, it's a force that opposes motion. So any force that opposes motion is called a resistive force. And it turns out that there are two types. There's surface resistive forces, and there's fluid resistive forces. Okay, so let's look at this thing. So any surface always has two forces. One of them we talked about them. We talked about the normal surface force is perpendicular. And that's what we just talked about a moment ago. But there is a parallel surface force. And the parallel surface force is parallel to the surface. And this parallel surface force is what we typically call friction. So a parallel surface force is friction. And so let's think about this thing. So imagine that I have a surface. Okay. And on the surface, I have a block. So I imagine that I have my block right here. And now when I'm looking at my block, I imagine that this block is actually moving in this direction. So the frictional force always opposes the direction of motion. And friction is symbolized by the little symbol F. So then we write F is in the opposite direction of this thing here. So what do we know about electrical forces here? Well, one of the things that frictional forces. What you'll find here is that this is the floor, and then this, of course, is our block. So to really understand what friction is, we look at the molecular surface between block and floor. And what you find here is that when you look at the structure of that surface here, it's actually quite jagged. So you could imagine that this, at this level, this guy here is the floor at the surface that we're talking about. On the other hand, when you look at the block, you also have jagged stuff like this. And so when you're looking at this surface right here, this guy here is the block. And what you're seeing here is that what you get in between these two surfaces here is that you get an electrical molecular interaction. And when you look at friction at this level, it is outrageously complicated. And you have to really be careful about the models that you try to explain what is going on. But that's what you're finding here is that when we ask in detail, what is friction? This friction, okay? That is friction. It's this molecular interaction between these atoms, and different materials have different interactions, and so therefore friction is different between two different objects. So you can see here is if this green block is sliding in this direction, then the peaks of the green ones are interacting with the peaks of the black ones. And so you have this relative motion between the two surfaces here. And it's this peak interaction that effectively gives rise to friction here. And what we find here is that there's two types of friction. There's one of them is called kinetic. In other words, moving, maybe I shouldn't say moving. I should say, when I say kinetic, I really mean sliding friction. And we typically symbolize this F for friction, and then we write a little K to tell us that we have this moving friction here. And what's special about this force here is that that this frictional force, so F of K is equal approximately to a constant. So sliding friction, kinetic friction, involves motion and it's constant. Then we have the second kind of friction, right? Static, which means it's random. And when we write this, it's typically symbolized with the S. And what you find about this thing, this is the really strange thing. Static friction is actually a variable force. And I should have said that this is approximately a constant force. And in the next chapter, we'll spend more time in trying to do that. So we talked about two types of friction. One type of friction up to this point. We said surface resistive forces. That's the kind of friction that we talk about every day. Now we have a fluid resistive force. And what you find next is that there's another type of friction called drag. And in fact, our next two labs are on this drag force, which is typically symbolized D here. This drag force, this here, it's a resistive force. The resistive force of an object moving through a fluid. And there's many fluids that we could think of here. The two most common ones is, of course, air resistance, the drag force of air, and the other one is water. And so what you're going to see here is that in our next lab, by the way, just to make sure that we're clear about this, outside of the physics stockroom in the 800 building we have a big box there, and we've put out numerous coffee filters and Hot Wheel cars. So if you're interested in picking up coffee filters, you'll see that you'll have to get a stack, and we're going to look for I think you're going to need 5 coffee filters, but that's to set up for the next 3 labs here in case you need those things. Okay. Yes, air resistance is the same as this drag force. So drag and air resistance are exactly the same. Is that what you're going to do here is that we have these big coffee filters. And when you're looking at these coffee filters, you're going to drop them in air. And what you find here is as you drop these in air, what you'll see here is that you have air molecules. So as this thing falls, what you're seeing here is that you're getting numerous collisions with the air molecules. So what you're finding here is that air drag is due to the numerous collisions between an object and the air molecules. Okay, so you have numerous collisions between these guys, and that's what produces that. The same thing if you're moving through water. Yes, the box is in the 800 building. Yes, it is. And the room is 802. So it's outside of 802 where these things are going to be located at. Okay, so I'm done with talking about forces here. So now what I'm going to go do here is that I'm going to move into Newton's second law.